Hello everyone, and thank you for getting up early to come to see this presentation. I'd first just like to start with thanking the session organisers for inviting me to present this work. And I'd also like to thank my co-authors, particularly the folks at University of Sao Paulo and University of Manchester, for providing data with which to evaluate my model with. Okay, so I'll get started straight away. So I'm sure you're all familiar with the impacts of biomass burning aerosol. I just thought I'd go over this quickly. So we know biomass burning as aerosol can impact the climate directly by absorbing or scattering sunlight, also indirectly by modifying cloud properties, and also particulate matter from fires, or PM2.5, has been linked with adverse effects on human health. So it's clearly important to understand biomass burning aerosol and accurately represent biomass burning aerosol in models. However, because of the high temporal and spatial variability in emissions, it proves very challenging to quantify the emissions and also challenging to represent them in models. And a result of this, previous modelling studies have found a persistent underestimation of aerosol optical depth observed in tropical biomass burning regions, and they've required a scaling factor to be applied to the emissions in order to capture the magnitude of observed AOD. And here are just two examples of these studies. Two papers where scaling factors of around 4 to 5 were required to capture AOD over South America, which is the region I'm mainly focusing on. In addition to this, the Aerocom group of aerosol models also find a consistent negative bias in absorption aerosol optical depth over the Amazon region. And these two model discrepancies may or may not be linked, but I think it's important to highlight both of them. So the reasons for these model discrepancies. Most modelling studies attribute the reason to an underestimation of biomass burning emissions, so for uncertainties in the derivation of biomass burning emissions from satellite data. But there are also many other reasons that could be responsible for this underprediction of AOD. And I've listed some of these reasons here. And that's really what my work is about, is to try and investigate these reasons in a little bit more detail. And to do this, we're using a global aerosol model, the Tomcat GLOMAP chemical transport model, which includes aerosol microphysical processes. And we're using in situ aerosol observations in addition to AOD to evaluate our model and try and better understand biomass burning aerosol. And this will lead to better estimates of the impacts of biomass burning aerosol on climate and air quality. So I've tested 3 different biomass burning emission inventories in our work. So GFED3, FIN, and GFAS 1.0. There are many different differences between these emission inventories and how they derive their emissions, but one key difference between GFED and the other two is that GFED uses the MODIS burn area product to derive the emissions, and FIN and GFAS use active fire observations. And this means that those FIN and GFAS are more sensitive to small fires, and we'll see an example of this later in the talk. This map here shows the measurement stations that I've used data from. So mostly the data is from Arana, so this is aerosol optical depth. But I also have surface PM2.5 measurements from 4 ground stations in the Amazon region. So there's Portobello and Alta Floresta, which are located in the deforestation arc of the Amazon, so they're highly impacted by biomass burning emissions. Then Santarém in the northeast of Brazil, also impacted by local biomass burning emissions. And Manaus, which is in a relatively preserved forest site and impacted by long-range transport of biomass burning emissions. So I'll get straight onto the comparisons between model and observations. So shown here, we have modeled versus observed monthly mean PM2.5 concentrations at each of those stations that I've just shown on the previous slide. We have the model simulation without any fires included, and then one simulation for each of the emission inventories. And you can see straight off that we get a strong improvement in the agreement between model and observations just by including biomass burning in the model. And overall, you can see that the correlation and the normalized mean bias is relatively good between model and observations, with fires included. We generally capture the seasonal cycle and the magnitude of PM2.5 at these surface stations reasonably well. If we look at a summary of the normalized mean bias over the 4 stations for each of the model runs. We can see that the mean, shown by the circle, is relatively close to 0, which is what we want. We want 0 bias in our model. And so the agreement is relatively good, although you can see with the GFAS and GFED emissions, we slightly underpredict surface PM 2.5. Something here, I'm just going to concentrate on the next slide, is an underprediction of GFED at this one site in Santa Rem. And here I've focused on this. We again show model and observed monthly mean PM 2.5, and this is for all months where there is data for. And we can see dry season in the red, wet season months in the blue. For GFED, we have a strong underprediction of dry season PM 2.5, whereas with GFAS and FIN, you can see a better agreement with the observations. And these two, again, I'll stress that these two fire emissions inventories use active fire detections to derive the emissions. And so it is likely, using a study by Randerson et al., which shows a small fire fraction of total burnt area, it is likely that GFED is missing small fires in this region and therefore underpredicting surface PM 2.5 at this station. And the reason I highlight this is because if you're scaling your emissions up by a factor of 3 or 5 to capture AOD, the scaling in this region won't make any difference really to the GFED emissions because there are no emissions to scale. Okay, so on to evaluation against aerosol optical depth. So this is again modeled versus observed monthly mean AOD at all the Aeronet sites that I showed in the map previously. Again, you see a strong improvement when we include biomass burning emissions in the model, and the correlation between model and observations is reasonably good. However, if we look at the normalized mean bias for the 3 regions, you can see that particularly for South America and Africa, we get a strong negative bias in the model, and this bias is larger than the bias was for PM 2.5 in similar regions in the Amazon. I'd also like to just highlight that different emission inventories perform better in different regions, and you'll be able to see that in these figures here. So how do we reconcile the difference between a strong underprediction of AOD and a reasonably good agreement with PM 2.5 at the surface? So I've done some sensitivity studies where I've scaled the particulate emissions by a factor of 1.5 and 3.4 to try and capture the observed AOD. And I want to look at the impact on surface PM 2.5 concentration simulated by the model. And here it just shows, again, the normalized mean bias at each of the 4 ground stations. And if we scale the emissions by around 50%, you can see the median here, the median normalized mean bias with the FIN emissions is at 0. So we get good agreement with the observations. GFAS and GFED may be slightly below 0, but the agreement's not too bad. If we start scaling by a factor of 3.4 or more, in fact, we get an overprediction of PM 2.5 at the surface. So if we look at the same simulations but compare with observed AOD, we can see that by scaling by a factor of 1.5, we can only really capture the magnitude of AOD observed in Southeast Asia with the FIN fire emissions, and we still get an underprediction in South America and in Africa. If we scale by a factor of 3.4, we can start to see improved agreement in Africa, some overprediction with the FIN fire emissions in Southeast Asia, and some improved agreement in South America, although we do get some overprediction at some of the Aeronet stations. So how do we try and understand this? We get good agreement with surface PM 2.5 with a relatively small scaling, but this remains some negative bias still remains in the modeled aerosol optical depth. And so to look into this a bit further, we've evaluated the model against aircraft observations of organic aerosol and black carbon aerosol from the SAMBBA field campaign in 2012. And you can see that for this phase 1 of the campaign, which was relatively polluted, there perhaps is some underprediction of aerosol aloft. So this is organic aerosol here. But in fact, in this phase 2 of the campaign, where concentrations were relatively low, it was fairly unpolluted, the model is actually overpredicting the observations in the vertical profile. If we look at the eastern region vertical profiles, so shown here by these flight tracks, we can see there is some evidence of the model underpredicting the black carbon fraction of the total aerosol, but there is certainly no strong indication of the model underpredicting aerosol aloft. So there must be some other reason for this additional underestimation of aerosol optical depth, and we attribute it more to the uncertainty in the calculation of aerosol optical depth rather than the vertical profile of aerosol concentrations. I now just briefly want to go through some potential implications of scaling your emissions to match aerosol optical depth measurements. So here we can see annual excess mortality estimates caused by biomass burning over Brazil for the GFED simulation in blue, and then the perturbed GFED simulation, so times 3.4 in red. And this is over years from 1997 to 2011. And perhaps if we can look at the average over all years, we can see a little bit more clearly that by scaling your emissions up, you can, your estimates of excess mortality from biomass burning goes up by around a factor of 3. And we've already seen that by scaling emissions by a factor of 3.4 overestimates surface PM 2.5 with the GFED emissions, so therefore this would be an overestimate of excess mortality due to biomass burning. So just to wrap up and summarize what I've presented today, we've shown that different biomass burning emissions perform better in different regions. Secondly, we've shown that to capture the magnitude of surface PM 2.5 concentrations, we only need a scaling factor of around 1.5, and this is potentially, well, this is obviously a lot less than previous studies have shown by only using aerosol optical depth. And scaling to match AOD may then result in overestimation of surface aerosol concentrations, and then this has implication for calculating health impacts of biomass burning. Thirdly, we found that to capture AOD in the Amazon region, for example, we need a slightly higher scaling factor than to capture surface PM 2.5. Comparisons with aircraft vertical profiles suggest that this isn't solely due to an underprediction of aerosol aloft, and is probably more likely due to the uncertainties in calculating aerosol optical depth in the model. This just leaves me time to acknowledge Aeronet for providing data for the comparisons, and also to acknowledge our funding from NERC. And I'll go back to my summary slide, and I'd be happy to take any questions. Thank you.
Questions for Carly?
So, have you thought about looking at the sensitivity of your AOD calculated in your models besides?
We have thought about it, but we haven't done it yet. Yeah, so we have some size distribution measurements from the ground stations as well. For a couple of the years, we have PM 2.5 measurements. So we've done some initial comparisons, but they've been really preliminary, so we haven't really concluded much. But yes, that's the next thing, to try and look at the size distribution and constrain that. Thank you.
My question is very similar.
Okay.
You didn't explain in the models how they treat the size bins or whether they're moment methods or anything. So for instance, if you have a 3 micrometer diameter particle and it should be a 4, and your cross section in that regime is R squared or D squared, you're going to have 100% offset. And that's going to more than compensate for this. So it depends how you bend them and how you size them. Can you explain that?
Yeah, so we use a modal scheme to represent the aerosol size distribution, so it's a 2-moment scheme. So we have probably the accumulation mode is probably more impacting AOD. So we could, yes, evaluate this against some size distribution observations, and hopefully that would give us a clue. Yeah, thank you.
Okay, thanks again, Carly.
Thank you very much.